Today, we consider the Legendre transformation, kind of transformation which is used for changing the basis of description from one set of variables to a new set of variables. Okay, so we have a function which is a function of one set of variables, and we want to change it to another function which is a new set of variables. So this is what is done by Legendre transformation. So let's see what we are doing. Consider a function of two variables, f of x, y. F is a function of variables x, y. So one can write df as dou f dou x dx, dou f dou y dy, and df can be now written as u dx. If we are writing dou f dou x as u, one can write this as u dx, and if we are writing dou f dou y as v, like this, so we have v dy. So df is equal to u dx plus v dy. Okay, now we need a function which is a function of u and y. Okay, f is a function of x, y, and we want a function, or we construct a function g which is a function of u and y. And it is defined by this equation g equal to f minus ux. So that where g is a function uy, that is equal to f, which is a function of xy minus ux. Okay, so we construct a function, or we define a function g, which is a function of u and y. Okay, and it's written g as equal to f minus ux, where f is function of x and y. So dg, that will be equal to df minus u dx minus x du. We apply the product rule here. Okay, so we are taking dg. So dg as df minus u dx minus x du. Okay, so dg is now equal to df. Df, what is df? Df is this, where u dx plus v dy, that is df. Okay, so we substitute for that, and we have dg as equal to u dx plus v dy, and this is minus u dx minus x du. So we get dg as we can this get cancelled, u dx this get cancelled. We have dg as equal to v dy minus x du. So y and u changes. So g is a function of u and y. Okay, and also since g is a function of u and y, we have dg as equal to dou g dou u du, dou g dou y dy, because g is a function of u and y. So as we compare these two, we have x as equal to minus dou g dou u. Okay, x as equal to minus dou g dou u, and if we compare dy, this part, we have v as equal to dou g dou y. Okay, so this is actually the Legendre transformation. We are transforming the function f, which is a function of x and y, to a function g, it's a function of u and y. Okay, which is written g, that is written like this. Okay, now this is the Legendre transformation. This has applications in many areas like thermodynamics, and then we will see how we are using the Legendre transformation in the classical mechanics. Okay, the Legendre transformation is frequently used in thermodynamics. Suppose we have this relation in the thermodynamics du, the internal energy, that is as equal to TdS minus PdV. This shows u is a function of S and V. Okay, du equal to TdS minus PdV. U is a function of S and V, and we can write du which is dou u dou s ds dou u dou v dv. Okay, and when you compare, we can say t is equal to dou u dou s, p is equal to minus dou u dou v. Okay, now through Legendre transformation, we define a function, or we generate a function h. It's a function of entropy and pressure, which is defined like this: h equal to u plus pv. Okay. So if you define h as u plus pv, when you take dh, you will have du plus p dv plus v dp, as you apply the product rule here. And for du we know which is originally tds minus p dv. For that we give, so for this du I am giving tds minus p dv, and this will get cancelled, and we have tds plus v dp. Okay, so h is a function of s and p. dh is tds plus v dp. And since h is a function of s and p, we can write dh. We know what will be dh. Dou h, dou s, ds, dou h, dou p, dp. And as we come back, we have the t as equal to dou h, dou s, v as equal to dou h, dou p. So the important thing here is, instead of this function, which is a function of entropy and volume, what we have is the enthalpy, which is a function of entropy and the pressure. Okay. So this is what we have here. Now we are considering the transformation, the similar kind of transformation in the classical mechanics. We have the Lagrangian, which is a function of q dot and t, generalized coordinate, generalized velocity and time. And we are transforming from this function to another useful function, which is going to be the Hamiltonian, which is a function of q, p and t. So instead of q dot, we have p here. Okay. The Lagrangian, we know that's a function of q dot t. So we can write dl as dou L dou qi dqi plus dou L dou qi dot dqi dot plus dou L dou t dt. A sigma I is there, that is implied there, it is there. Because the q involves q1, q2, qn, q dot involves q1 dot, q2 dot, qi dot. Okay. So this is dl. We have n variables. Now we define the canonical momentum as pi as equal to dou L dou qi dot. Okay. The pi is the canonical momentum. Pi is equal to dou L dou qi dot. Okay, we define like this. So from the Lagrange's equation is d by dt of dou L dou qi dot minus dou L dou qi. This is equal to 0. Dou L dou qi dot is now pi. Okay, so d by dt of pi, that will be equal to dou L or dou qi, or pi dot will be equal to dou L dou qi. So we substitute for that. So we have dl for this dou L dou dou L dou qi. I am substituting. So we have this pi dot dqi, pi dqi dot plus dou L dou t dt. Okay, so this is the dl. Okay, this is dl. Now we apply the Legendre transformation and we define the Hamiltonian like this: h function of q, p and t, which is sigma I qi dot pi minus L q t. Okay, we define or generate the Hamiltonian, which is a function of q, p and t, whereas L is a function of q dot and t. Okay, so we have this, and we take dh. Dh will be, if I take dh, that will be equal to qi dot dpi and qi dot dpi plus pi dqi dot minus dl. Okay, so qi dot dpi plus pi dqi dot minus dl. Okay, this is plus. Now for dl, I am substituting from here. For dl, I am substituting from here. I am writing pi dot dqi plus pi dqi dot plus dl dot t dt. So that we substitute here. And as we substitute for that, we have this, and this will cancel. This term will get cancelled. Okay, and we have qi dot dpi minus pi dot dqi minus dl dot t dt. This is dh. And since h is a function of q, p and t, we define h as a function of p, q and t. See, dh is, it varies with the pi, it varies with qi, it varies with dt, so h is a function of q, p and t. We can write dh as equal to sigma I dou h dou qi dqi dou h dou pi dpi dpi dou h dou t dt. So as we compare, we have here we have dpi. So dou h dou pi is qi dot. Okay, dou h dou pi is qi dot. Dou h dou qi is minus pi dot, and dou h dou t is minus dou l dou t. So we write those equations. So dou h dou qi, that is minus pi dot. Dou h dou pi is qi dot. Okay, and we have also minus dou l by dou t as equal to dou h dou t. And these equations are known as the canonical, Hamilton's canonical equations of motion. Okay, canonical equations of motion, Hamilton's canonical equations of motion. Okay, so these are very important equation to us. Dou h qi dot is equal to dou h dou pi, pi dot is equal to minus dou h dou qi. Okay, Hamilton's. So we have 2n. Since for each variable there are n variables. Okay, I varies from 1 to n. So there are 2n equations here, and all of them are first order differential equations. So we have a set of 2n first order differential equations replacing n second order differential equations. Okay, so instead of n second order differential equations in the Lagrangian, we have a set of 2n first order differential equations. So using the Legendre transformation, we define the Hamiltonian function, okay, from the Lagrangian, and then we arrive at the canonical, Hamilton's canonical equations of motion.